you've got your microphone on. Good. Let me do a little bit of AV setup here. Yeah. Oh, okay, good.
Oh, we've got another 5 minutes.
Lots of time.
There it is. Okay. Oh, perfect. Perfect. Okay.
Are we ready to go with?
I'll get it back in just a second.
Yeah.
Okay. Yours was.
That one, yep. Do we have a slideshow button somewhere?
Of course, this is in Danish.
Viz, maybe? Yeah.
I think that's. No. This one?
Yeah, what, very bottom one. Maybe. No, no, wasn't that.
Can.
It's a loop.
Just let me get the clock on. So as folks are coming in, a reminder, the evaluations, please consider filling those out as the sessions, as you watch the sessions, rather than waiting till the end of the conference. We really need your input to make sure we understand what worked and what we can improve on. How many are going to the event this evening? Good. Some people are going to the event this evening. That's good. So what we'll do is we're going to have 3 speakers, and the speakers will present for roughly 25 minutes, and we'll have about 5 minutes for questions at the end of each presentation. And we'll start. Get my little clock out here. We'll start in about 1 minute. And Clive Davenhill is going to talk about their advanced circuit reservation software. For those of you, when we get to the question and answer period, I'll ask you to raise your hand. We'll get the microphone to you. You have to hold this microphone really close to your mouth. And that way it's captured on video, and the streaming session people can hear the question. You don't do that, they really can't hear the question. So thanks.
Right, well, good afternoon, ladies and gentlemen. I hope you can all hear me. As Steve said, I'm Clive Davenhill. I'm from the National Youth Science Centre, which is part of the University of Edinburgh. And in many ways, I stand before you as an imposter, because until a couple of years ago, I was a programmer rather than really a network person, and remain basically a programmer. And what we're going to be talking about for the next half hour or so is perhaps a slightly different view of light paths and dedicated circuits, or particularly dedicated circuits, looking from the outside looking in at how they might be controlled rather than controlling them from within. However, as I said, I started out as a programmer and then encountered the famously impenetrable jargon of networks. And before we started properly, I thought, just might look back briefly at the first definition of net in the English dictionary a couple of 100 years ago. If that's the definition of net, then it's hardly surprising that the definition of networks has become equally impenetrable. Anyway, enough of that. What I'm going to talk about, well, briefly, is the Easily circuit reservation software, and the talk is divided into 3 parts. The first of which is the oh, we have a pointer. Excellent. The first of which is the Easily project. I'll say a few words about the project itself. Then a few words about the problem we're trying to solve, to look at, and then a bit about the circuit reservation software we derived. So, first of all, the project. As it says in the first bullet point, it aims to demonstrate the use of circuit switch networks in high-performance applications. And the little picture I put up there at the right, I put up partly because it amused me, and partly to make a number of points, which is that circuit switched networks have been around for a long time. That's the Paris Telephone Exchange in the 1890s. And secondly, they were normally, many times in this conference and elsewhere, think about them in terms of light paths and high-capacity light paths. They can actually be implemented or simulated in a number of different ways. What Easily was about was using high-performance networks, in this case, really the modern optical networks, running over them new applications, doing real science. And in that respect, we had a number of disparate groups who collaborated to work together. These came from, deliberately in fact, came from a variety of scientific disciplines. The principal investigator I ought to mention is Peter Clark, who can't be with us today. The project ran for 2.5 years. It's now coming to an end, and it was funded by those UK funding bodies. That quickly, we'll just skip over this. That's a list of participating groups. But as you can see, there are a variety of institutions listed there, and in many cases, there are several groups in each department, in each university, as well as the traditional high-end users, such as physics and astronomy, who are doing a variety of particle physics and astronomy things. There are also, well, here at Oxford, there are people working on e-health applications, health applications automated over the internet, and advanced large interactive simulations in the chemistry department. Within Easily, we ran a number of sub-projects, which are quickly listed there. There was high-energy physics and radio astronomy that Arpad told us about a couple of days ago, and the other ones I mentioned. In addition to those, there are a couple of final projects, the capability development projects, which aim to develop facilities that would be useful to the various application disciplines. And everything that I'm going to say this afternoon came from the final capability development project, so-called control plane. As I mentioned, we had this variety of groups scattered throughout the UK, with collaborators overseas using high-capacity networks. In the UK, we had this thing called UK Lite, which is basically has been set up over the past few years, providing dedicated circuits, which, unlike the normal internet, people have to apply to use in a prompt and informal procedure. And that provides a number of 10 gigabit connections across the country, and also connections to overseas. The circuits are basically SDH circuits rather than controllable light paths, but again, you nonetheless get full use of the circuit. So now briefly talk a bit about the problem we were trying to solve. I rather like that quotation at the top there from Andrew Tannenbaum in his Computer Networks, which I think in many ways encapsulates a lot of what we've been saying over the past couple of days about light paths. There's obviously a great deal of interest in them, and they provide many useful capabilities. But nonetheless, there's also, because of the success of the packet-switched internet, a degree of suspicion, shall we say? So basically, though the packet-switched internet, as you all know, has been incredibly successful, there are now numerous scientific disciplines that require very high network performance, of which, the ones I mentioned are examples. And again, as we all know, you can have dedicated circuits as an alternative, and these can be simulated as well as being direct circuits. Simulated with things like GMPLS or translated across technologies and so forth. Now this is another one of my famous diagrams. That's on the right there. That's the London Telephone Exchange in the 1880s from the London Illustrated News. I do rather like that picture. If you just look at the top of the corner there's obviously the magic piece of paper with the magic instructions written on for the things you really need to do that aren't in the manual. I can identify with that. Currently in UK Light and elsewhere, the circuits are configured, well, quote unquote, manually. That is, they're provisioned by hand. And as we heard this morning, this can lead to long setup times. It can take, well, best days to provision them. In practice, usually longer, given the vagaries of planning work in ahead. And circuits provisioned in this way rarely last less than a few weeks, and are often permanent or quasi-permanent. Now, of course, there are many applications for which that's fine, because you have a continuing need, and the facilities you're running are essentially expensive enough to justify having permanent circuits. The radio astronomy EVLBI work certainly falls into that category. They have long observing runs, and even if when they're not observing, they can still use the circuits for testing and so forth, so they can certainly justify full-time circuits. And things like the Large Hadron Collider and the other particle physics experiments fall into much the same category. On the other hand, there's another different class of users, particularly those in the working on simulations with supercomputers, whose requirements are really rather different. Often they will set up experiments on supercomputers that last a few hours or so, possibly even a shorter length of time, sometimes longer. And they'll be doing distributed simulations, distributed calculations, which require linking two or more supercomputers and will require significant amounts of data to be transferred between the machines for this couple of hours that the experiment runs. Now, it's really obviously rather difficult to provision manually circuits in that way if it's only going to be used for a couple of hours. What we really want to be able to do is to provision the circuits automatically, and moreover to be able to schedule them automatically in advance. So you have a sort of booking system, and you book an hour or so, 2 or 3 weeks or months in advance, at the same time that you book the time on the supercomputers, so the three things come together at the same time. So that really was the sort of problem we were addressing, and I'll now briefly say a few words about the software we wrote to investigate this problem. So, as this slide says again, the main aim of the work was to allow us to develop a system that allows circuits to be set up automatically and that provides advanced reservations. What we have basically written is a demonstrator, a proof of concept type thing, but it's also, we hope, going to be of use to the the participating projects, participating groups, and some of their follow-on projects. This is, I should emphasize, a very, very schematic view of what the network looks like. The thing inside the orange-brown box is an extremely schematic and now out-of-date view of UK Light. And around it are machines which are under Easleys control. These are, as I say, this is UK Light with its fixed SDH circuits which are configured manually. On the outside are basically, in the hatched boxes, Cisco 7609s, which we inherited from a previous project. And around them are clusters of end hosts, PCs, which act as the sources and sinks of the data for the various sub-projects. And there are also, as you can see, links to overseas. And finally, we had an additional 7609, which was attached. Well, we had the circuits so configured that they ran from the end hosts to the simulated core switch, and then out again, so they could be stitched together. Yep. To produce this booking system, we developed the circuit reservation software, CRS. We deliberately didn't write it from scratch. It's a modified version of the BAR, Bandwidth Allocation and Reservation software, developed by the EPCC, mostly developed by EPCC in Edinburgh, as part of the GRIDS project EGEE, which again we briefly heard of earlier in the meeting. And the main people involved in the work are listed there, and I'm not going to attempt to pronounce their names. And also a number of external collaborators that they worked with, including Dante. BAR was developed for quality of service over conventional networks, and we modified it to handle our dedicated circuits. Also, as I should also mention that for one of the components that I came come onto in a moment, we used a modified version of Salim Bharti's NRS, Network Reservation System. Salim and his colleagues were originally at UCL, and he's now at St Andrews. The original EGE bar, which was developed by, well, was part of EGEE, really too many E's in these acronyms, was written in Java. It was a distributed system, which the components communicate via web services. So this was all running on straight Linux PCs, which, in our case, talk to are attached to the conventional internet, and they send commands to our 7609s to configure our network, which of course is, let's say, this is a demonstrator. The modified version uses those two databases mentioned there, Postgres and HSQLDB, and as I say, we use a modified version of Salim Bharti's NRS as two of the components. Now this, which perhaps is the most important slide in the talk, is the architecture of of BAR and CRS, and it's worth taking a moment or two to talk through it and work through it. As you can see, it's a distributed architecture, and each of these components communicate via web services. So at the very top here, we have a user running a client, or in BAR terms, higher level middleware, which can be an interactive browser which he uses to make reservations, or it can also be some piece of grid middleware. For example, a co-scheduler that will be co-scheduling the network at the same time as it's co-scheduling the supercomputers that the experiment is going to work. So it can be driven manually or automatically. Then working down the stack here, the first component we talk to is the so-called BAR component. Now, the idea of this is that well, an instantiation of this would be run typically by yourself or your own group in your department, in, for example, a chemistry department here at the DTU. And what it maintains is a list of databases, a database of reservations, bookings that you've made inside your department. Now, the bar component communicates really with potentially three other components: the LNSAP, the bar, the remote bar. I haven't shown the line of communication here. The remote bar, which is its opposite number at the other end of the circuit that you're trying to set up across the network. So, for example, if you were here in the Danish Technical University in Denmark, and you wish to collaborate with colleagues in the University of Streslau, the bar would be running in their department in their university. Now, the bar, as I say, communicates with three components: the so-called LNSAP, NSAP, and this remote bar. The LNSAP is typically run by, or would be typically run in a real deployment by the computer services group at your local university, and that too has a database of reservations that it knows about. And the important point here is the LNSAP. It's the LNSAP ultimately which controls the local network. Now, in our demonstrator case, the local network was simulated by 17609. In reality, it would be the local campus network, or that small fraction of it which is providing this sort of service. The NSAP is a similar sort of idea. Again, it has, like all these things, a defined web service interface, which the bar makes a request of, and beneath that it configures the sets up the circuit, ideally in the wide area network of in the fashion that was discussed as being how desirable people were working towards this morning. Okay, so what happens when a user makes a reservation? He types his requested reservation into the client here. The web service request is sent to the bar, which checks in its own list of reservations, bookings that exist. It also sends a request for to the LNSAP, the local network, sends one to the NSAP, and sends a request across to the remote bar. If each of these answer back yes, then yes, we can make this circuit at this time. That's okay. Then the reservation is added to the database, and the user is told the reservation succeeded. Well, if they can't, then it isn't. Obviously, it isn't added. Now, the point here is that the bar is communicating with a remote bar, which in turn talks to its LNSAP rather than your LNSAP, this bar here talking to the remote LNSAP directly. The reason for all this is to allow for trust and control, because when you set these things up, you can trust your friends in the remote chemistry department, and similarly up to a limited amount, your computer services department will trust you, whereas they won't trust random people across the world. So basically, the architecture is all about allowing distributed components to allow trust. Right, as I say, what we've written is a very simple demonstrator. Both of these components, the LNSAP and the NSAP, just control 17609, which is clearly unrealistic. But what we would imagine is that, given we have defined interfaces here, it is possible to simply write backends for these components for whatever networks you're trying to control. So that basically is that. Where are we? Well, most of the software development is complete. I'm writing the manual. We're in the middle of trial deployments with some of the groups. We have a chap who's developing a more complex version of the NSAP, which will be a pilot interface to Canary's UCLP as a more realistic attempt at a network than a single 7609. And we also have plans for driving the whole system from the HARC co-scheduler, which is used by the reality grid people. As far as deployment's concerned, well, we're hoping that some aspects of the system will be used in a follow-on project, but we shall see. And finally, I don't know how we're doing for time, but fine. This is my last real slide. Just a few brief words about enhancements that I had to make to the standard interface that EGE had defined. The first point, support for queries. The original interface, perhaps slightly surprisingly, didn't support named queries at all. You couldn't make a query of the sort of the type, tell me all the reservations that discharge between, or should discharge between this date and that date, or all the reservations that are going to discharge between these two end hosts, i.e. typical database type queries. The only supported type of query was tell me information about this reservation whose identifier I already know, which is fine in some contexts, but I felt was a bit limited for a browser. So I added a rather more flexible support for queries. As a deliberate decision in EGE, they specify the software so that it doesn't give the user any notification when the reservation discharges and its circuit is set up. Now there are good arguments both for and against that, and that was the decision they came to. But I think perhaps there's a case for revisiting that argument. Something else that it would be good to have is provisional reservations, both between the bar and its subsidiary components, the NSAP and the LNSAP, and also between the client and the bar. Now you might wonder why you would want such a thing. Well, basically in a world where everything's free, there's no particular advantage. You can just make the individual reservations and then reserve that, then cancel them if it turns out that either the bar can't line up the other components or that the co-scheduler can't line up the supercomputers at the same time. You've made them, you can cancel them, it's just a few minutes later and nothing's lost. However, if you live in a world where you're actually charging for some of these things, then you really want to be able to make reservations provisionally for a few minutes whilst you get yourself sorted out and then confirm them. Otherwise, you'll just be incurring charges unnecessarily. And finally, EGE introduced quite late in the project, I believe, the notion of reservations and activations. As you can see there, activations were subdivisions of reservations. And this was done, I think, for purely pragmatic reasons, because of the length of time that it actually took their systems to set up some of the reservations and set up some of the equipment, which was done manually in their pilot. And again, that was entirely understandable, and there's a case for it. But it does make a lot of the interfaces a lot more complicated than they would otherwise be, and there's a case for talking through that again, I think. Not necessarily changing it, but certainly talking through the justification. And that's me. What I should have mentioned at the beginning, but forgot, was those are the other people who are involved in this work. Thank you.
So, do we have questions for Clive? Actually, I have a question for Clive. I'll start off with a question. So, what was when the 7609s were configured, what configuration parameters were applied? What QoS mechanisms were
Oh.
actually implemented?
Well, obviously we sent, the way it worked, it sent a series of iOS commands, of course, and we're really doing things quite simple to do with VLANs, just setting up and enabling VLANs.
Okay, so you're just essentially configuring VLANs. You're not doing any priority queuing or...
No, it's very simple, and because it's a demonstrator, that's all built into the bottom component, so it doesn't matter.
Gotcha,
Yeah.
gotcha. Other questions? Going once. I know it's after lunch.
Everyone's fallen asleep after lunch.
Yeah, everybody's falling asleep. That's why they serve beer here for lunch. Okay, thanks a lot.
Ah, right, yes.
So Gerard from Nortel is going to tell us about Ethernet, which is my favorite protocol. I've always thought it's Ethernet all the way down, and that's a good thing. So let me.
You can even do it down there.
Oh,
Perfect.
okay.
Thanks. My name is Gerard Jacobs, Gerard Jacobs. When I was following several of these presentations today and yesterday, I became more and more aware that it's a rather weird, odd thing to talk about Ethernet. Because the people already talking about what will happen to SDH, which is a rather new protocol. People already discussing when it will be phased out. Ethernet is a protocol which was introduced more than 30 years ago by Robert Metcalfe. It was a new invention at that time, and I'm more than 30 years after, I'm presenting on it again. And basically what we're asking ourselves is Ethernet going to have a new life, especially related to the wide area network. And that's where my presentation is focusing on. So what will I address? I will address why do we still talk about Ethernet? Do we have to talk about Ethernet? What is carrier Ethernet? That's a variant that is introduced to cope with all the challenges that we see in the wide area network. I will dedicate some slides on the standard process. Where are we? What is standardized and what do we expect? Then I will discuss some aspects of provider backbone transport. That is the latest addition to IEEE standards. It's the QAY standard. The name, in fact, comes from a collaboration with British Telecom, but the real standard name is PBB Traffic Engineering. Then, of course, a summary. So why are we still interested in Ethernet? The reason is that everybody seems to be interested in Ethernet. In a OIF discussion session very recently, Level 3 discussed Ethernet, and they came to the conclusion that it is a protocol, it's a service that is wanted very much. And they saw in 2006 a 30-fold multiplier with respect to the number of 10 gig Ethernet-based interfaces and services bought compared to the SDH 10 gig interface. So it is an interface that has a lot of attention in the industry, and it's becoming rapidly a very much wanted service. We also see that it is a protocol that already has a long life. It is everywhere deployed in the local area network. We see also that it's heavily commoditized. And that is, I think that is what we have to contribute to the very rootless specification that the IEEE all the time performs. Ethernet is in detail specified. It doesn't leave room for options, and that makes that everybody can manufacture it. And that's what in fact happened. You know, there's a lot of manufacturers that productized Ethernet, and that's why it really became a commodity. We see also that Ethernet is a very interesting technology. It is a connectionless medium. It means that broadcast, unicast is inherently embedded in Ethernet. And what we are trying to do is, by tweaking around with the broadcast and filter capabilities, we can tweak it in such a way that we also can provide dedicated point-to-point links with SLAs, and we will see that later. And what is very interesting is that the complex packet technologies that we have nowadays, like MPLS, they are very interesting from a technology point of view, but from operations point of view, they are sometimes a nightmare. And especially with fault finding, providing the right SLAs to your end customers, there is a very much skilled staff required to really find out where the mistakes in your network are and how and to operate. And the last but not the least point is it is the cheapest technology that we have in the industry, and that is what all the time very much appeals to people. So what is the vision of Nortel? As you can see on the left hand, there are several layers in the network. Here I have put 6. Many people who operate a network have a variety of this, less or much less than this. But what we are in fact looking at is trying to collapse the middle section from SDH up to MPLS in one layer. And we think as Nortel that you can do that in an Ethernet, with an Ethernet technology, the combination of PBB, provider backbone bridges with PBT. This is what we are, in fact, are trying to do in the industry. So if you look at carrier Ethernet, what carrier Ethernet started, I think in 2001. That's when we first introduced it in the market. And the challenge that we had at that point is to extend the LAN over the WAN. And in fact, in order to do that, you really need to dedicate all the items on the left-hand side. You need to dedicate some attention to scalability. For a little bit more than 4,000 VLANs is by far not enough for wide area networking. There is a issue with security. MAC learning is a major issue. It's a flat layer 2 network, meaning that the core of your network has to learn all the MAC addresses in the entirety of your network, including the ones on the enterprise, and that's what we don't want. Another aspect is, of course, reliability. When we started Ethernet, it came out of the enterprise, and enterprise has a different perception of what reliability is than public operators. So there was some work to do there as well. And then the last 2 points are very much looked at lately, the last 2 years, and that's quality of service and SLA. How do you find faults in your network? Sorry, not finding faults in your network, but trying to define the quality of your circuits in your network. And how do you, in fact, provide a guaranteed performance to your end users? And the last aspect is the OEM. That's where how do you find faults? What is and how do you provide the right tools to find these faults? So what was introduced is what we call at that time MAC and MAC. It's providing a Ethernet UNI. That was in fact something that was stolen from the ATM frame relay world. So what you basically do is that you define a user network interface between the core of your network and the customer. And by doing that, you in fact separate the core of your network from the enterprises. So the enterprise information is tunneled through the network, and the core of your network is not bothered, influenced by what people at the enterprise do. In the meantime, you get a much better convergence of your network, meaning much higher reliability, because you do not have to cope with millions of MAC addresses, but only with a few hundred or maximum a few thousands. What was introduced was a much higher scalability. Instead of the 4,000 VLANs, there was a VPN identifier, ISIT, we will see later, introduced, and that has a scalability of 16 million. And 16 million VPNs basically means that you have enough for a large network. So this is the standard that is almost about to be finalized. It is called PBB, Provider Backbone Bridges. And what it basically does, it adds a Ethernet header on top of your Ethernet frame. And in that Ethernet header, as you can see, you have the destination and source address, ether type. And then, of course, you have the 4096 VLANs, the backbone VLAN ID, and that is used to specify the different qualities of service that you have in your classes of service that you have in your network. The ISIT, like I already said, is the 16 million that you use to discriminate between all the different customers that you have in your network. The nice thing is that this is very nice in building core networking. You can even use a spanning tree, which is a rather weird protocol, but with the 100 or 1,000 MAC addresses that you maximum have in the core, even spanning tree becomes an interesting and nice protocol. These are the services that the Metro Ethernet Forum has defined. It's ELAN and E-line. E3 is about to be defined by the Metro Ethernet Forum. ELAN is in fact an extension of your LAN over the WAN. So you can operate the different LAN sections that you have as if they were one virtual large LAN. E-line is also a very interesting proposition that defines a point-to-point connectivity. Initially, within PBB, it is very hard to specify what really happens in the core of your network, meaning that you can not provide a strict service level agreement, because you can only shape and police at the edge of your network, but in the core of your network, as it is a connectionless medium, that is not possible. The reason why E3 is very interesting, that has to do with the hub-spoke functionality that was already provided by Frame Relay ATM, and there is definitely a need for that kind of architectures in the business world, but also with respect to triple play applications. This is a very interesting and heavily implemented architecture. So where are we with the standards? Like I said, this is the way it started. We not to introduce the Mac in Mac concept in 2001. We started the discussion in IEEE in 2004, and it is about to be finalized as a standard. The next phase, which is the PBT, the Provider Backbone Transport, which is basically PBB plus the capability of engineering deterministic circuits, that is in fact captured in PBT, and that is now also standardized in a draft, and that's the QAY. And that's what you see in the next slide. This is the standard summary that is relevant to Ethernet. So first you see the 802.1ab. That is a auto-discovery standard which is heavily implemented. It's widely spread, and we use that to discover the network as it is running. Then we have the AD, the provider bridges, which is a approved standard. Then we have the AG, which we will later see is key for connectivity fault management, so finding your faults in your network. Then we have the AH. That is a standard that is about to be finalized. We expect it's going to be at the next meeting in June or July. Then we have the QAY, that's Provider Backbone Bridge, Traffic Engineering. That is the official naming for PBT. That is it's now an official draft. A few months ago it was approved. So we expect that a stable standard will be available by the end of the year, and it will be finalized by the end of next year. because that's what you most see in standardization with IEEE. There is half of the time is spent on really defining what should be in the standard, and then the other half is spent on defining and making it a strict, very rigid specified standard. The ITU is also of importance with two standards. It's the Y1731. That is very important to provide the right performance monitoring. We as an industry have learned from that. SDH has served a big need. They have defined very interesting standards, which we in fact are borrowing for Ethernet again. So what these standards provide you is with frame loss, frame delay, delay variation. Then we have the Ethernet protection. As we will see in the next part of the presentation, with PBT is trying to emulate emulate SDH on an Ethernet network. And to do that, we also need to have the same kind of 50 millisecond protection. And that's what we borrowed from the G8031 standard from the ITU. So what is provider backbone transport? Provider backbone transport is a new standard. As you can see, it is a little bit awkward naming, but that has nothing to do with Nortel. That's introduced by the IEEE. It's a new kind of nomenclature for all standards that are currently implemented and are a draft. In fact, PBT, as I will call it, because the QAY PBBT is too much, it's too long of a name. So let's name it PBT. PBT is basically a point-to-point Ethernet tunneling technology, and in such a way that you define explicit the performance of that tunnel end-to-end. So it's a trunk in your network, and in that trunk you can define a lot of VPNs that run point-to-point. And you can guarantee the performance. It's like SDH. It's just a circuit from point A to point B. You can also have, like you see with the purple trunk, you can define backup trunks. That backup trunk can be a one-to-one replacement for the working link, but it can also be the same standby trunk for other point-to-point links. So the capacity of the backup doesn't have to be reserved all the time. You can use that for other services. It is also possible to switch to the backup trunk in 50 milliseconds. So what we are basically doing is that we are defining SDH-like guaranteed performance and SLAs on an Ethernet network. And tests, trial implementation have shown that the performance of such a trunk is exactly the same as the one you expect from SDH. And one of the more rigid applications, which is synchronization recovery in wireless networks, are seriously considering using this kind of technology, because you can recover your synchronization over such a PBT-based network. So how do we do that? What we basically do is that the PBT functionality is built on top of the AH functionality. And what we are basically doing is that we don't switch, we don't have an independent VLAN switching Ethernet switch anymore, where every VLAN switches on the destination address. What we basically do is that you combine the two. You combine the 48-bit destination address with the 12-bit VLAN that you have, and you come up with a 60-bit long discriminator. And if you, it's the combination. So what the VLAN becomes from a global parameter becomes a local parameter. And what we do is that, contrary to what we do most in the industry, we add functionality and we add complexity. Basically what we did is that we turned a lot of functionality off. We basically learned that all the MAC learning we turned off, no broadcast, no spanning tree, no flooding of unknowns. And if you turn that off, you populate your forwarding database with the management. And the forwarding is based on what kind of explicit routes do you want through your network. The nice thing about IEEE is that the specification of how to turn off broadcast and multicast, how to turn off MAC learning, how to turn off spanning tree is all specified so rigidly that you can basically mix and match all vendors in such a network. We have done large-scale trials with our equipment, with the one from our competitors, and it works. The only thing that is not specified yet, very rigidly, is the flooding of unknowns, and that is done in the QAY standard to make sure that every Ethernet switch that you have is capable of supporting that. So how does it really work? First, you have a network, neck and neck. You have U and I's on the left and on the right hand side. You have probably a Q and Q handoff to an MPLS network or another Ethernet network. And what you do then is that you basically put it under management, but not such that the management determines how the network looks like. We have come to the conclusion that you should ask the network. The network knows best how it looks like. So what we basically do is that we use the 802.1 AB, the auto discovery standard, in such a way that the network discovers itself, and it in effect tells the network management how it looks. And that makes provisioning and adding of nodes much simpler than we currently are used to. So what you do next is that you can define some trunks in your network, and those trunks are you define over which node you want to have them, over which fiber connections, and the one can be the backup of the other. What you do next is that you can also define a backup trunk, in this case the purple one, and what you basically do is that you force your traffic from the left to the right over the green trunk by looking at the combination of destination address and VLAN. And that makes that for PBT, you only have to reserve maximum of 10 VLANs on a global scale, because you can reuse all VLAN numbering at every node, because it's a local parameter and not a global anymore. So what we also do is that we introduce 802.1 AG control frames, and they are inserted at the receiver, the destination address, and they travel back to the destination address. So what PBT basically does is that instead of having unidirectional paths, you have a bidirectional path, the same as we have in SDH. And as soon as there is somewhere a fault in the network, being it either a system or a link, then immediately the switch on the left-hand side switches to the backup trunk over in this case the purple link, all the traffic. And that can be done in 50 milliseconds. And basically, tests have shown that you can do it between 30-40 milliseconds. This is a very realistic time. So what is the other nice thing about how and basically the question behind this is, how do you operate a network with PBB and PBT? So it is a very interesting technology in the sense that it's managed by VLAN. So what you basically can do is that per VLAN you can either choose to have an any-to-any connectivity over PBB, or you can have a PBT functionality with a strict end-to-end performance on the link. So what you see is that per VLAN you have either a spanning tree or other mechanisms for resilience for a PBB connection, but PBT, because it's VLAN oriented, it totally ignores that state. And the same is valid for an MLT state of a port. And it means that you can explicitly define over which trunk, over which link, over which fiber you would like to have the PBT trunk running. Then I would like to discuss something else. As you can see in this slide, the perception is that an optical network is managed in a different way than the data packet layer. And what we see in reality, if you talk to operators, then you see that optical networks are rather simple to run. You don't need a high-skilled staff. It is a self-explanatory network that explains to you what is wrong. In IP/MPLS, we all the time struggle with really finding where the fault is. You need highly educated experts to do that. It's almost an art to find a network in a complicated IP/MPLS network. So the reason behind it has to do with what you see in this slide. The industry has decided, on the bottom you see MPLS, the IETF has decided not to be bothered by too much things that have to do with OEM. They are definitely not interested in the whole discussion on performance monitoring, but there's also only a limited functionality available with ping and trace of tools that are available to locate the faults in your network. What we're basically doing in Ethernet is learning from especially SDH and the ATM world of some years ago. So what we basically do is that we have the fault management now specified in a very strict draft already, the AG standard, that is focusing on trying to find a fault with pings and trace tools. But you see also that we use the ITU standard, the 7031, to come up with a detailed specification of how the performance is of your network. So you can, like we had in the past, error seconds and things like that, you can now define frames loss, delay of frames, delay variation of frames, which is comparable to what we had in SDH era. And this makes it possible for Ethernet to emulate SDH, like we know it today. Here you see it again. Okay, almost finished. So there's some key elements to OEM. It's the AG, like I explained, it's the 7031, but it's also the 8031 for protective switching, the AIS indication that we are implementing that in Ethernet as well. And of course, like I said, auto discovery is very important. That makes the whole management, provisioning of your network much easier. So the summary is, what we did in making a LAN technology really have a second life in the WAN world is building upon these three pillars. First, it's the provider backbone bridges, already heavily deployed. It scales to millions of users. It's a customer separation. The core of your network doesn't have anything to do with your CPE. You see also that provider backbone transport is in addition to that. It makes it possible to emulate all SDH that you have today in the future on an Ethernet network, and it brings the same characteristics, like connection-oriented, traffic engineering, explicit routes through your network, and also explicit guarantees. You can provide not only on demand, but on an unsolicited demand from your customer, you can provide them with detailed performance data. And then, of course, the third pillar is the Ethernet OEM. You know, it's very important to have the right tools to manage your network and to provide people with statistics on the performance of the network. And that's it.
So I have an initial question while people think about their questions. In terms of supporting large MTUs, what do the standards allow for, and what is Nortel looking at in terms of implementation?
The MTUs, now we are up to 9600 jumbo frames, and I think that's what the industry is looking at as well.
So inside the core, so I can have customer payload that is that large, and so there can be slightly larger frames in the core.
You need a larger frame for the encapsulation. And that's what we support now. It seems that the industry is going that way.
Okay. Questions?
Is anyone else implementing these two standards except Nortel?
And participating in these standards?
Sorry?
Is there anybody else than Nortel participating in these standards?
No, implementing them.
Yeah, everybody. That is the amazing thing. You know, the amazing thing is that up to the end of 2005, Nortel and Hitachi were the only ones that implemented anything that had to do with Mac and Mac or Mac and Mac-like implementations. The beginning of 2006, we saw a heavy adoption of Mac in Mac. The only one who didn't adopt it yet, I'm not sure if I can mention it, is a company like Alcatel and some other minor small ones, but the big ones, Extreme, Cisco, all these companies have adopted these standards. You can have Mac and Mac implementations from many customers. Unfortunately, it's Nortel is the only one that implemented large networks based on Mac and Mac end to end. But the industry provides you with whatever, except maybe for a few. And you see that, the AH standard is jointly developed by Nortel and Cisco, and we see the same happening now with the QAAY. The QAAY standard was initially there was a move. We tried as an industry to make that a subsection of the AH standard. We didn't succeed in that. That was vetoed by Alcatel. We succeeded now as an industry to find a new standard, and even Alcatel is supporting that standard. So at least the industry, in its entirety, has accepted that this is a way to go.
Taking this as a final comment from your side, can you further comment on the relation between PBT and TMPLS?
Yeah. We
talking about major industry trends and standardization efforts.
Yeah, TMPLS proves to us that we are in fact on the right track. If the implementation that TMPLS is mainly pushed by Alcatel, if the current solution of Alcatel would be the right solution, and it would offer a solution to all your problems, then why invent TMPLS? What TMPLS in fact proves is that the arguments that we had in the beginning is that MPLS is a rather complex but also expensive technology is the way to look for an implementation on Ethernet. And what it basically does is that TMPLS recognizes that. The only problem is that TMPLS is that, as you probably know, that the 8110 standard that defines the TMPLS is an ITU standard, and it's incompatible with the MPLS standard, which is defined by the IETF. So now you have two discussions on things that look the same but are not the same at all and cannot talk to each other. And it's questionable how long it will take before that really gets solved.
Time for one more question before we move to case. Any more questions? Thank you very much.
Thanks.
Can you stay in this area?
I'll try.
Yeah, try. Okay.
I'll do my best. I need to stick that somewhere.
Yeah, in your pants.
Is this high enough or should it be higher?
Yeah, maybe. But it must not,
Doesn't work? Let's stick it in my beer.
So we're going to hear from Kees de Laat on what's going on with Lambda Grid, Starplane.
Okay, thanks. Is the mic on? Okay, now it is. Okay, I'm going to give you an update on Starplane, which is Dutch Science Foundation funded project trying to utilize optical photonic switching in the nationwide backbone in the Netherlands. So here you see the typical logos of funders, except one who is not standards compliant apparently. This slide has often been showed, so I thought I show it also myself. Nowadays, the backbone traffic on ARM6 and so on reaches values like 250 gigabit per second and more, which is also a clear need for and a clear stress for the Ethernet environment which ARM6 is deploying, by the way. But the talk today is about this curve and what we do about the C-class and to some extent the B-class traffic. So I'm going to talk about applications which really are in the C-class and see how you can most effectively, most cost effectively, most most flexibly provide those applications with the bandwidth they need, which is typically 10 gigabit and higher. I have given talks about this model of that you have class A users, which typically use normal email, normal day-to-day internet, which is usually up to ADSL speed, whatever the ADSL speed is. That needs routing. The B class, which is typically virtual or real organizations where a lot of traffic stays within a confined boundary, up to gigabit Ethernets or 10 gigabit Ethernets, which typically can be handled with layer 2 technology, and this was typically the stuff that you would deal with optical photonic switching. I now also know which logo this is. This is actually the University of Amsterdam logo. That's funny. Okay, always test your slides before you come up to this stand. We had also yesterday a slide not working in one of our talks. So what the hybrid networking is all about is basically creating an infrastructure where you can separate traffic which needs routing because it has to go anywhere on the internet, traffic which can live in layer 2 environments, and where PBT, as from the previous talk, would be also something to certainly seriously look at, and traffic which is really point-to-point from telescope to correlator or from LHC accelerator to a tier 1 institute or these kind of things. What you also see here is kind of scale, metro scale, continental scale, world scale, transoceanic. And you have also different technologies which are deployed on those scales. And there's also a different kind of flexibility you typically have on that scale. If you own the fibers in a metro or in a nationwide area, you can put in whatever your equipment and gear can do and make that infrastructure flexible. But if you need to cross the ocean, then you know there is just so much flexibility you can build in there, because technology to get photonic signals across the ocean is anyway already complicated. So you usually nowadays still end up with some technology. So the talk today about our nationwide photonic switching experiment is typically this box. It's where SurfNet owns the dark fiber. SurfNet owns the DWDM equipment they put in, and now wavelength select switch. So I'm going to explain you actually the physics of it a little bit for dummies. And so what you can do in this box on a reasonably small scale, where you are not too much bothered yet by a lot of regenerators and all kinds of protocols sitting in your way. So I'm going to talk about this box in this framework. This is the Netherlands. This is actually the dark fiber footprint, what SurfNet has acquired over the last few years. And you see here typically the university cities and the cities where there is also a city dark fiber infrastructure, a Gigaman and so on. Groningen, so you see here Amsterdam, Leiden, Delft, and then back to Amsterdam via where our nation broadcasting company is, so Hilversum. And the experiment I'm going to talk about is roughly in this ring. You also note that the size of the Netherlands is actually not that big. So measured in round trip time over fiber, it is about 3 by 2 milliseconds. So you can say that the Netherlands is about 6 square milliseconds big. You see here that, well, SurfNet connects about 180 organizations, institutions, research centers, and also polytechnical schools and so on. The total infrastructure is about 6,000 kilometers. And if you also go to the railways and ask how many railway tracks do you have, they have also about 5,000 or 6,000 kilometers of railway tracks. So you see that these nationwide infrastructures have about the same scale. So this is more the way the optical photonic network is implemented on that dark fiber I showed in the previous picture. It is split up in about 4 or 5 rings, depending how you count. They start in one location in Amsterdam, which is actually on our campus of the University of Amsterdam, or the Amsterdam Science Park. The POP is at Supercomputer Center Sarah. And there's another pop on another place in Amsterdam, sufficiently far away that power failures do not usually touch both sides, so that there is a kind of backup. And then the rings go from one side to the other, and there's also dark fiber between those sides. And so this is currently the implementation, implemented with Nortel CPL technology, which allows, if you use the 50 gigahertz filters, up to 72 lambdas per fiber. In that's 8 lambdas per band, and you can have 9 bands of colors on each fiber. So with Kees Neggers, I had a discussion about a few years back, so two or 3 years back, about that photonic networking was nice, but that you should also aim for some flexibility. So we had a discussion about that, and we saw technology coming like wavelength selective switches. I'm going to explain that a bit later. So we thought up of an experiment where we would, on this green ring, where Amsterdam, the Free University, Leiden, Delft are involved, cooked up an experiment where we would dedicate one of those 9 bands of lambdas just for experiments with dynamic real-time photonic switching. So where you would be able, from a grid application, to tell to the network what kind of topology you want for the next distributed computing task. I will also come back to some of those tasks at the end of this talk. As it happened to be, there is a consortium in computer science in the Netherlands between 4 universities. That's Amsterdam, Leiden, Delft, and the Free University, which is a distributed ASCII computer consortium. And that is that are groups which, so once every 4 or 5 years, together buy 5 compute clusters, combine them in one big and then wide area coupled cluster called DAS, connect them up, and then do all kinds of distributed computing experiments. That was started that work about 10 years ago by Andrew Tanenbaum, and now Henry Balfour from the Free University is chairing that part. So at the same time, we put in a proposal called Starplane in the Netherlands to do the dynamic photonic switching part between those 5 clusters. So that is basically then the logical picture of Starplane. We have these compute clusters. I will go in more detail how they look like, but you have compute clusters. They have some kind of local switch. In our case, now it turns out to be a MiriNet switch as a fast interconnect between the blades, about 70 to 100, depending on which side you look. And then connect them with up to 8 times 10 gigabit to a device at SurfNet, which makes from these 10 gigabit Ethernet connections colored connections, so just translates one color into another, just two transponders, so to say. And that goes into the ring. And at the ring, there are, at certain places, wavelength selective switches, which have then the capability to dynamically change where the color goes to. So a color can go in one instance so red can go from Delft to Leiden, but then we need more capacity for whatever computational reason to another university, and then the wavelength selective switch can change the path of that color without going to the electrical domain again to another university. So the idea is that from the grid environment we can tell the NOC via, currently it is by phone, fax and hammer, but in the future you want to use web services or something like that to signal, listen, in the next minute we need this topology between that cluster. So you can imagine that in one instance you typically want a tree structure to send out data to all nodes, and then you need next neighbor communication, you want a ring structure, for example. So we want to be able to signal the network as a kind of extended backplane of the computers. These are basically computers with backplanes. So we want to regard this as a kind of under program control or under grid control configurable extension of our backplane. Now, how does that work? So what kind of devices are coming on the market to make this vision possible? This is the way how a wavelength selective switch would work. Works in principle. You have incoming fibers, and each fiber can contain up to 80, so a full ITU grid worth of lambdas. So there can be 80 different colors in this fiber. Now it goes through a lens, and then it goes to a diffraction grading, which is basically kind of prism, if you wish, or so the colors come out under different angles and are projected here on a MEMS device, which is basically just a kind of chip with micro mirrors, where the mirrors can tilt a little bit under control of software. So each mirror gets one color out of one of the input fibers. And then it is just a trick of selecting which color you want to have in the output fiber, tilting that mirror to the same grading such that that color gets out here. So out of this outgoing fiber, you get a selection of a mix of the colors of the incoming fibers under control of software and this MEMS device. Switching goes very fast, basically, because these mirrors, just like normal glimmer glass or those MEMS devices which can do that switching, a KDN switch, for example, can do that switching in about 10 milliseconds. It takes way more time over the control plane to talk to such a box than to change the path of the color, of the lambda. It is also true that this is slow switching, so it is not per packet switching, but you basically change a complete lambda. It is also slower, of course, than optical burst switching, if you would compare it with that. But it is, of course, faster than any normal rewiring or reconfiguration as it is done today. So in the Starplane project, there's now one band of lambdas, and there are at this moment 4 of these wavelength selector switches deployed to allow changing the passes colors take through the infrastructure, and that is in a production network. So this is on exactly the same fibers and exactly the same infrastructure where all the universities along that same ring get their normal internet connectivity. So if we do anything wrong here, then you know I will get very famous in the Netherlands of knocking out a few universities. But we have put filters in place, there are filters in place and so on, so that everything what happens with these wavelength selector switch stays confined in that band which is dedicated for this experiment. So we are pretty safe. Another thing, which is also a piece of technology which is needed to make this possible, is electronic dispersion compensation. If you have a fiber of sufficient length of hundreds of kilometers up to thousands of kilometers, then the speed of light in fiber is actually slightly dependent on its frequency. And if you modulate the signal, so modulate the lambda, then it actually has a certain width, so it has a certain frequency range. And so the higher frequencies travel a little bit with a little bit different speed than the lower frequencies, and it is very tiny, but the signals are also very tiny in time. So after hundreds of kilometers, if you send out a very nice squared optical signal, on, off, what you see on the other end arriving at some point is not the nice eye diagram anymore, but there's some wobble, some irregular pattern from which it is hard to reconstruct where the zeros and ones are. So Nortel has over the last years come up with a device which they call electronic dispersion compensation, for which I have here for dummies in 5 steps how that works. So what you try to do is to find out the transport function, so the dispersion function, the transport function of the fiber. And then, so suppose that you can find it by try and error, just like an old audio modem in a telephone system would do by sending different tones, and then you know till it gets a good signal. You invert that transport function, and then computationally multiply that inverted function with the Fourier transform of the bit pattern you want to send. So if this is what you want to send, you take the Fourier transform of this one, multiply it with that inverse function, and then you get a signal, and what you get out of that, you transform back to time space, and you get some wobble, and that is what you are going to send. Now, if you send that, then that will be, of course, convoluted with the transport function of your fiber, and what happens to be is that what you get out is exactly the original pattern, because the distortion and how this distorts actually cancel each other. So to make this happen, you need to be able to compute these steps in silicon, and then be able to modulate the laser in phase and in amplitude to make this signal. And those innovations were done last year, and that's what's actually going on in an electronic dispersion compensating modem currently. And that means also that if you have currently, for example, a caller going to a nearby university, you change the wavelength selector switch to go to another university which is 1,000 miles further away, then these modems can retrain or remember, like, oh yeah, I did that yesterday also and I needed these parameters. It can immediately flip also to the dispersion compensation, and then the signal can be received by the other one. If you don't have that, and you would not be able easily to do that with the old fiber tricks. Also, you may notice that this looks exactly the same as that. That's not just a lazy cut and paste of me, but if you really look into it, this is the power spectrum, which is the square of the signal. What dispersion does is change the phase, and the phase drops out if you go to the power spectrum. So they are really looking the same if you look in a power spectrum. Then there is a challenge of sub-second switching. If you currently look at bringing up and bringing down lambdas in CPL and in these photonic systems where there are many lambdas deployed already, it takes minutes. And why does it take minutes? It takes minutes because most of these systems actually also partly already existed 10 years ago and so on in some incarnation, and were used in the telco sector. But telco said, well, okay, I want to be able to bring up a lambda, and if it's on, that's fine. Then it should be solid with 5 nines, and we keep it there for 10 years, and then we go to another business or out of business. But nevertheless, they do not want to flip that around very often. So, so that was fine. However, we are now looking really at the other edge, where under program control, within a few round trip times in hundreds of milliseconds, I can flip a lambda under control of grid software. So that is in the other edge. So I asked actually the question, usually in the collaborations, what in physics prevents us from doing it way faster? Because currently most of those minutes go into, okay, I turn up the laser a little bit and then I read out how all the signals are doing, and then I change the filters electronically a little bit, and that whole tuning process is automatically done, and that they do that currently in minutes. So we are currently working with Nortel, or Nortel is working with us to get this time, this lambda turn on and turn off time really short. And so there are ideas about how that is going to happen. There is also a plan B for us. If it is really difficult to get this down to the sub-second part, because I want to go to sub-second photonic switching here. For the intermediate time, we have also a MEMS device switch on this side, where it is just black and white light and so on, and on the university side. And this one we can, of course, flip as fast as we want, and in milliseconds and so on. This is how the computer clusters look like, which were acquired by the 5 universities in spring of last year, and which are now received and commissioned. Lots of blades, 10 gigabit MiriNet on this side, where now we also have blades in the MiriNet switches. They were just last week, and this week they are delivered and turned up with the 10 gigabit Ethernet ports on this side, which is then connected to the Starplane stuff. And here we have also, for management and other file sharing purposes, also a normal 1 or 10 gigabit connectivity to the university side. Actually, the DAS computer clusters, DAS has several meanings in Dutch. DAS in Dutch is also a tie, that's also called the DAS. And then there is also this animal, which also carries the name DAS. So that's why you see a DAS with a DAS. A DAS, so a badger with a tie. So what we try to work on in this project is quality of service in a non-destructive way. So let me explain you what destructive quality of service is. And that's, in my opinion, everything what happens most of the time to now. You have a lambda, and in that lambda you set a part of it aside for the lucky few which you want to give a higher priority, and so the rest is squeezed to a smaller place, because you know the purple and the red gold get this quality of service. So constructive quality of service, in my opinion, is you get this transparent optical photonic environment. You have a lambda, but you know you need more transport. So you add other lambdas by switching them in with wavelength selector switches. You move the lucky ones over to those new lambdas, and the rest get also a bit happier. So this is what I call constructive quality of service, and that's what Starplane is about. So from the grid point of view, this is also quite an exciting time. As it used to be up to now in the grid, global grid forum and all those projects, is that a lot of research is done on CPU and data co-location and scheduling. So where is my data and where are CPUs? What is the cost of the CPUs? And oh yeah, this network is also there. You can never rely on it, and it is always I cannot influence it. And maybe it works, maybe it will not. So it's always congestion prone and so on. So they use the network as a kind of dirty constant, but they try then to co-schedule CPUs and data, and that's extensively done always in the past. What we are now going to able to do is also to influence with lambdas the network. We can now specify the network, and that becomes also a function in the cost function, where you do your scheduling and your co-location and so on. So this gives you this gives you a three-dimensional world where then to find a sweet spot for your grid applications and for your e-science applications. So the Starplane vision is to give the flexibility directly to application by allowing them to choose the logical topology in real time with sub-second switching times on part of SurfNet infrastructure. So what makes Starplane fly? So one thing what I explained to you is the low-cost photonics of wavelength selector switches. To give you an idea, so if you would do this all with routers, a wavelength selector switch costs about 100K in any currency list price. A router port costs you also 100K, also in any currency, and if you phone them you get of course rebate, so they both come down. So for me, for the sake of discussion, they cost equally much. However, the wavelength selector switches can, of course, switch around way more bandwidth, but only point-to-point, compared to one router switch. So the amount of bandwidth you can play around with wavelength selector switches is way more, and also it saves you a lot of transponders, given that the new modems are going to be able to, or are able to really traverse hundreds to thousands of kilometers. Another thing which makes this possible is the sandbox construction we have on that production ring to make sure that the experiments we do not by accident knock out other lambdas where production traffic for universities is running on. Optimization of controls to turn on and off lambdas. So the control environment, which is DRAC for that part, and how to talk to DRAC with web services and SOAP and so on, is a thing which makes it possible. The EDCO, I have explained that. Traffic engineering we need to do, and we are currently also looking at open source GMPLS, the Dragon code, and working together with Internet 2 to see what can happen there. We have had first light last week actually. We had Starlight deployed now between, or Starplane deployed now between a number of hosts on location of Free University, University of Leiden, and our university. You see here round trip times, which are of course extremely constant, and you see here a matrix of nodes which we are now able to talk to each other, and these are round trip times. And here you see then the bandwidth, which is what basically those protocol stacks without too much optimization could reach. Is 6 gigabit on the 10 gigabit passes, and UDP a bit more. So this is, so basically this is first light. The first things are starting to flow, and so it is working. This is just to give you an idea of what we collectively can do with the 5 clusters on the different locations, from Leiden, Delft, UVA, the Multimedian cluster, and the Free Universities. And it's nice to take here the totals, then you see what we are talking about in terms of total storage, total number of gigahertz. So we have, if you count all the clock cycles for all the CPUs, we have 2 terahertz of multiplications word equivalent. And but you also see that if the MiriNet and everything that aggregated, we can produce now 320 gigabit per second out of DAS 3, and now we of course claim that SurfNet is a bottleneck again. Power is a big issue. I learned that the hard way when trying for the location for our cluster and so on. So if I look to the UVA cluster, which has 85 blades of compute blades, then it uses as a max 30 kilowatt per hour. So let me guide you through this calculation. 1 kilowatt hour is about 10 euro cents in the Netherlands. So if you multiply that by the number of hours in a year times 30, you get about 25 or 26 kilo euro per year, 26,000. Well, if you put somewhere a kilowatt in a room, you need also to get it out. That takes about half of that same amount of power. So that inflates this 26 to 39 by adding 13 kilo euro. Then you need also to do something on emergency power systems for if the power drops that you can add it. That inflates the number a little bit more. So you see that a rack currently, and this is 4 racks, so that 10 kilowatt hour is now normal. However, if the total cost for power of this cluster is 50k per year and the whole cluster costed about 400,000 or 500,000, then you see that over the lifespan of 4 years of this cluster, you burn about half of the cluster over its lifetime. So if we score, for example, in Big Grid 30 million from the Dutch government, which we actually scored, then you can just already say, okay, this will be an electricity bill of about 5 million. So we should actually be supported by the power companies, I think. Also, terminating fibers costs power. So terminating a 10 gigabit wave in a router interface takes about 200 watt. You can find that it is some, so Juniper and Cisco numbers are around 250, 280 watt, and maybe there are also less power consumption per wave interfaces. I do not know for sure, but that gives that an entirely loaded fiber termination costs you about 16 kilowatt. Well, if you would be able, if it is just switching for complete lambdas, if you can get away with that with a part of your traffic, and that you only need a few routed interfaces and that you can keep a lot in the lower layers, wavelength selective switch is just a few watt. I have 1 more minute. Oh, well, it will be tough. So we are working on the AAA part. So we have done a demonstration last year at supercomputing where we do the slow and the fast part of the authorization part, separating by tokens, and then the tokens travel with on the data plane in the signaling messages, and can make sure that everything you need to do to get a pass set up is only done locally, so that it doesn't need to go out via slow web services to user home organizations or ADR home anymore. Control plane, we are currently busy with DRAC web services into place and making sure that we can do this signaling. What's very important here is also to be able to describe the topologies and reason about topologies and play with topologies. So yesterday there was a talk from Paola Grosso on this subject. You can download it and see it. So we are just working on a semantic and RDF-based model to describe these networks and their relations. So describe the topologies and their relations with other networks where each domain keeps an RDF file of its resources and interlinking that. Our ultimate vision, and this slide was unfortunately yesterday not to see, but now it's fixed, it shows on this stupid PC. Our vision is that currently we are able with XML and with RDF to describe topologies in network domains and do path finding. We can show that. Supercomputer Center has done these kind of tricks for a complete SurfNet, for path finding and so on, based on RDF. But we are also working for the SceneGrid community to do the same with storage. That's our vision. We want to do that for transcoding or computing, for visualization, tile displays or 4K projectors. Also annotating content with what is in the content and describing that in RDF. And ultimately, our vision is that this will give us the capability to, on high level, ask a question to the system and then find in the RDF a reason about what infrastructure you need. And ultimately, you will find that I want this content, it's here, it is linked to this entrance, and I need to go here and here. And if you know these points, then path finding becomes trivial. So I can flash you a few applications, EVLBI, tile displays. This is a tile display with SceneGrid content, which are 7 gigabit streams if you want to do this. And this is about terabit. This is my last slide. Can I go through this one? So terabit thinking. So we are currently engaged in discussions about what is the next phase. Next phase, terabit networks. So we are currently thinking about what constitutes a terabit network. So if you, for example, we had these discussions called T square. That's why this example. It has 8,000 gigabit drops. Does that make call IT square an 8 terabit network? Well, that's I don't think so, because you know we have in Amsterdam 20,000 100 megabit ports. Is that then a 2 terabit network? No, it's just what you aggregate. Look, for example, at an 80-core Intel processor. If that would be working and you would cut it in half and see what left is communicating with right on that chip from Intel, then that is already 8 terabytes per second. So these amounts of terabits and terabytes of networking on the chip size is already possible. So we are currently having discussions how you can extend massively parallel from the chip level terabit networks up into backbones and onto these infrastructures. Think also back. So one of the things is that putting many links and then adding them up and say, tada, this is terabit, is not really what you need. If you think back to teraflop computing, there you would have 1 gigaflop PCs in racks. And what makes that a teraflop machine? MPI makes that a teraflop machine. So if you think along those lines, teraflops you get because of MPI and Globus and the many parallel things which you group together, like a bunch of PCs. So for terabytes, you use oxidides or other data handling systems which can play around with terabyte and petabyte objects, and that makes your terabyte storage and petabyte storage. Terapixels is by Sage, which makes your tile display work. Tera sensors, you have, you know, these are out there. What we really need is also to get our minds around what the MPI for terabit networking is, I think. Thank you.
Questions for Kees?
questions or coffee.
You kept them late.
Yeah, that's the problem. That's the question.
You mentioned the electronic dispersion compensation, and that's used for when the fiber length changes. But when does that ever happen? Fiber is normally twice fixed and steady.
Well, it depends. If you are going to do these MEMS device switches, then of course a laser talking to another laser may find itself at once talking to another laser which has a different path. So if these passes can change, and actually, I mean, these modems are not more expensive than, although I don't know the prices exactly, than having the dispersion compensation fibers in the fibers themselves. So it makes a lot of sense to do all this compensation in electronics if you can do it. But it also gives you then this flexibility if you want to build in wavelength select switches and MEMS device switches, which can also in principle change the lengths of the path the light has to travel through. So it gives you a degree of flexibility, and gives you also, I think also more freedom in what kind of fibers and what kind of dispersion. So you don't need to worry about dispersion compensation anymore, which is usually a huge tricky problem, as it turned out to be in SurfNet when those rings were constructed.
Anything else? Well, I want to thank our presenters again. Have a good coffee break.